Welcome to Study Loop.
Hi. So in this problem, it is given that we have a cable that is suspended and the load acting on it is a function of the distance from the lowest point, and the tension acting on the lowest point of the cable is T naught, and we have to prove that the shape of the cable is given by the double derivative of y is equal to Wx over T naught. And it is given that the if suppose this is the cable, then the tension at the lowest point is T naught, and this height of any point from the origin, like if the x and y coordinates are these x and y, then this height of any point is given by y, and the distance from the lowest point is given by x. Okay, so we have to prove this thing. Okay, so for this, let's take an element of the cable, not the complete cable, but a little part of the cable, so that we can apply differentiation equations to that part. So I take a part of the cable, a segment of the cable. Let this be the segment, and we know that a tension is acting on the cable in the horizontal direction, T naught, and simply there will be horizontal tension here, T naught. If this point is the origin, then not the origin, any point at which the vertical tension is a function of x, if x is the coordinate of this point, and if this distance is delta x, then the tension here is dy x plus delta x, because that's the coordinate of this point, the x coordinate of this point. And this distance is delta y, like the because it is element of the wire, a small segment of the wire. So if this point is at elevation 0, this would be at elevation delta y. So this would be delta y higher than this point, and this would be delta x ahead than this point. Okay, so let's solve for this, and we know that the cable is in an equilibrium, so all the forces present in the y direction should cancel out each other. So summation of the forces in the y direction should be equal to 0. Okay, so other than these two forces, one more force will be acting downwards, that is the weight of the cable, and we know that Wx is the weight per unit length of the cable. So this elemental portion of the cable will have weight equal to Wx into delta x. So let's write the equilibrium equations. So we get dy x plus delta x minus dy x minus wx. We are taking the upward direction as positive and the downward direction as negative. So the sum of these should be equal to 0. And rearranging the terms, we get dy x plus delta x minus tyx is equal to wx delta x. So let's divide both of these sides by t naught because that will make our differential equation. So let's divide both the sides by t naught. And and we know that the Ty is the vertical force and To is the horizontal force, and this will be the resultant torque, and if this angle is theta, then tangent of this theta would be equal to Ty over T naught. And this tangent is a tangent of theta is nothing but the slope of this cable. And slope can be given by rate of change of y with respect to x is equal to Ty over T naught. So now coming back to our this equation, we can let's separate these. We can write so put applying this equation number 2 into this equation number 1, we can see that this is not equal to dy over dx when x is x plus delta x, and this is minus dy over dx at x equal to x, and this is equal to wx over t naught. Let's take delta x at this side, so it becomes like this. Okay, so according to the different equations of the differentiation, we know that if we put limit of this, if we take the elemental segment and we take this delta x equal to tends to 0, then it will just give the instantaneous values of y with respect to x. So this term, if delta x tends to 0, will become the double derivative of y with respect to x, and then it comes equal to wx over t naught, and this is what we wanted to prove. So we have proved this, and we can write here hence proved. I think that's it. Thank you very much for following me.